Now, what if you are looking at a value, like we just talked about, that someone reported to you? How do you determine which digits are significant and which are not? Well, it turns out it's actually pretty simple, and there are 5 rules. Alright, so is a digit significant? Rule number 1, if it's not a 0, it is significant. For example, 2.38 milliliters. That has 3 significant figures, namely the 2, the 3, and the 8. Now, the wording of that rule might lead you to imply that it's the zeros that are the tricky ones, and that is the case. Rule 2. Zeros between digits that aren't 0 are also significant. So 2.308 milliliters. That has 4 significant figures in it, and the implication is that that volume is accurate to plus or minus 1/1000th of a milliliter. Now, zeros to the right of the decimal and to the right of the last non-zero digit, they too are significant. An example of this would be 2.790. So this 0 is to the right of the decimal point and to the right of the last non-zero digit. So that one is significant. So in combination with all of these, that has 4 significant figures in it. Rule 4, if a 0 happens to be to the left of the first non-zero digit, then they are not significant. This is referred to as a placeholder 0. So here's an example. 0.026 milliliters. That has, so these are to the left of the first non-zero digit, which is the 2 in this case. So that only has 2 significant figures, namely the 2 and the 6. Last but not least, zeros that are to the right of the last non-zero digit but are to the left of the decimal. So this typically happens with large numbers. So again, these zeros here are to the right of the last non-zero digit, but to the left of the decimal, and these are properly undefined. You don't know. The volume could be known to plus or minus 1 milliliter, or it could be that that 0 is just telling you, is there to tell you that that 5 belongs in the hundreds place. So the way that we make that clear is simply convert that to scientific notation. So if that volume really was known to plus or minus 1 milliliter, you would put it like this. If they were all significant, you would report it like this. And by turning this into scientific notation, these zeros get moved to the right of the decimal place and then become significant via Rule 3. What if they were just placeholders? Well, if this last one was merely a placeholder, then it would just be 1.50 times 10 to the third milliliter. And if there were both placeholders, you would just say 1.5 times 10 to the third milliliters, and then you would know that this has 4 or 3 or just 2 significant figures as appropriate. Now, what I will tell you is that generally, when it's a big number and there's a whole bunch of zeros at the end, usually they are not significant. They usually are placeholders, but properly, it's actually undefined. So the next thing I have to talk about is propagation. Now it turns out that when you measure something in the lab, what you directly measure is almost never what you need. There's usually math involved afterwards. So, for example, it would be a common thing for you to try to measure the density of something. Now, density is defined as the mass of something divided by its volume. There really aren't any density meters. But even if we can't measure it directly, that's not a problem because we have devices that we have balances that measure mass quite easily. And we have things like graduated cylinders that measure volume very easily. Measure both of these separately, do the math, and boom, density. Now, there's going to be, in any experimental measurement, there's some uncertainty. Because in almost every case, like with our ruler example, you're just measuring something, you're subjectively comparing something to a scale. And there's going to be, everyone's going to do a little bit differently. So that means that there's going to be some uncertainty if there's uncertainty in the mass and the volume measurement, that means that there's going to be some uncertainty in the resulting density. And we would like to know what that is. The true answer is obtained through differential calculus. Now, I'm happy to do this when I ask for the face-to-face classes. Usually they defer, so I will spare you that. But significant figures actually give you an idea, a way of at least ballparking what that uncertainty is, at least what the order of magnitude is. And that's nice because it depends on just two simple rules, much less worse than the differential calculus. Right. So, the two rules, and I'm going to use the density example for one rule and the perimeter for another rule. And a perimeter is simply the sum of the length of all the sides of something. If it were a rectangular or triangular object. And so if you're going to measure the perimeter of something, the uncertainty in the perimeter value is going to depend on the uncertainty of the length measurements that were made individually. So, two simple rules. That's it. Rule 1 talks about if you're multiplying or dividing something. And the rule there is that you simply propagate. The answer will have the smaller number of significant figures of all the measurements that went into it. So, for example, the balances that we have in the lab can measure something to 1/100th of a gram. And we've got devices that can measure volumes easily to 1/100th of a milliliter. So if I weighed an object and it told me that it had a mass of 12.97 grams and it had a mass of 3.26 milliliters, if you were to do this division in your calculator, you would get this number right here. And depending on your display settings, you might get more digits than this. Now, do you really know the density of this object to the 10th, hundredths, thousandths, 10,000ths, 100,000ths, millionths, 100? This implies that you know the density to plus or minus 1/billionth of a gram per liter, and that's simply ridiculous. So the rule is that however many sig figs the numbers that went into the calculation did, your answer should have that same number of sig figs. So this is a 4 significant figure value, and this is a 3 significant figure value. Between those two, 3 is smaller than 4. So the answer should be properly expressed to 3 significant figures. Now, a common question is, do you round up, or what do you do with that last digit right here? It should be rounded, up if necessary, or leave it as it is. So look at the third, the third sig fig. In this case, it's a 7, but the one next to it is 8. So this value is closer to 3.78 than it is to 3.98 than it is to 3.97. So in this case, it's rounded up to 3.98. Now, if this number right here would have been like a 4, then you leave it at 3.97. So if the next digit is is greater than 5, it goes up. If it's less than 5, it goes down. Now, if you are adding or subtracting things, the rule is different. In this case, what matters is the number of decimal places, and you go with the smaller one. So, for example, I've got a triangular object here, and for some reason I used a different ruler for one side. So I've got 3.24 centimeters, 6.78 centimeters, and this one here is only reported to a tenth. These are to hundredths. So the rule here, if you were to do this in your calculator, you would get this answer right here, 17.52 centimeters. And but calculators are dumb, and this one should actually be reported to in 2 decimal places, 2 decimal places, 1 decimal place. So that should be you should round that to, or it should be expressed to 1 decimal place. And in this case, since it was 5.2, then it just stays at 17.5 centimeters. Now, one thing I'll say is that it is very common to keep an extra significant figure in intermediate calculations to help with what is called rounding error. And that is an okay thing to do. When I'm looking at sig figs, usually it's just whatever your final answer is. I want to be sure that that is reported to the appropriate number of significant figures. But remember, there's just 2 simple rules depending on whether you're multiplying or dividing. The number of sig figs. If you're adding and subtracting, it's the number of decimal places. And in both cases, you're going with the smaller one. And one last thing with significant figures, and that is exact values. So these are things that essentially have an infinite number of significant figures because there was no estimation involved in determining them whatsoever. And they actually fall into 2 categories. One is counted values. So this is saying that there are 8 people in the room. You are doing that by simply counting people in the room. You are not comparing to a scale, where there's a picture of 1 person or 10 people or 5 people and saying, oh, it's about 8. So there is no uncertainty in there. A big one for this is that think about when you're taking an average of a bunch of values. How do you do that? You add up the sum of all the values, and you divide by how many values there were. That denominator, how many values there were, is a counted quantity. The other kind of exact value is something that's part of the defined relationship. So these are conversions within the same unit system. So we're talking about 12 inches equals 1 foot. That is a defined relationship. A inch is defined as a 1/12 of a foot exactly, or conversely, an inches. A foot is defined as 12 inches exactly. Now, the way I always treated these values is I was, just assumed that they had an infinite number of significant figures. And the end result is that they have no effect in a sig fig calculations. They will not be the limiting factor. So it's important to be able to recognize them so that you know that they don't matter with sig fig calculations. And one way to do this is just to pretend they have an infinite number of significant figures.